Hi everyone. So in this video, we're going to be learning the second part of the fundamental theorem of calculus. So as I mentioned in the last video, the first part of the fundamental theorem of calculus is really important for basically conceptual reasons. So the stuff we talked about in yesterday's video really kind of underpins a lot of what we'll be learning this quarter. However, we don't in practice use the first part of the fundamental theorem of calculus that much. What we'll be talking about in today's video, the second part, that is what we're going to be using all the time. So you'll find that this is a really useful theorem. So let's get into it. So I just want to kind of set the stage a little, just remind you basically what we have learned so far in terms of computing integrals and finding areas. So far, we only know how to find the exact value of an integral. So the exact value of an integral of a function for certain functions, right? So the types of functions where we can find the exact value are functions where when you actually sketch the region, it ends up being like a semicircle or a triangle plus a rectangle or something like that. So for certain functions, and I'll just kind of add that note, functions where the area can be calculated using geometry. So that's that. There are certain types of functions where we know how to find the exact area. But mostly what we've been doing in this class is we've actually been approximating areas, right? So for other functions, f of x, we have been approximating so not finding the exact area, but approximating the value of the integral of the function using Riemann sums, or rectangles, I'll just say. And we talked about in an earlier video how, technically the exact area is equal to this limit, right? So we know that the exact area So we know that the exact value of the integral is this limit idea, right? So if you take the limit as n approaches infinity of a sum, where you're basically, I'll write it down and then remind you what each piece of this means. But basically, this part in here is the area of each rectangle, right? Because xi, that represents, it's x1 and then x2 and x3. So basically you're plugging in different x values within different rectangles. And so when you plug those in, that gives you the height of the rectangle, and then delta x is the width of the rectangle. So f of xi times delta x is just the area of each rectangle. Then if you zoom out one level to here, now remember this sum symbol means you're adding up. So now we're talking about the sum of all of the different rectangles. And so that part would be an approximation. But then if you take the limit as n approaches infinity, so now looking at this whole thing, you're basically then going from, adding up 5 triangles, rectangles, 5 rectangles, 10 rectangles, 100 rectangles, you're bringing that number of rectangles towards infinity. So we do actually, we know theoretically how to find the exact area. However, that's not usually convenient to calculate. So we actually, as I mentioned, I think in some Calc 2 classes, you'll actually spend a good amount of time working on evaluating limits like that. I've just found that, especially in a summer quarter, it's just, there isn't quite enough time to really give that topic enough time to do it well. So that's why I don't really spend much time evaluating these limits. But anyway, I just wanted to say that, it is possible to find the exact area using these limits. We just haven't really done it. And it, generally speaking, is not very easy. So I'll just say that these limits are generally rather difficult to compute. Okay, so all of this, why am I telling you all of this? Just to kind of set the stage for what we're about to learn. So today, we will learn how to find the exact value of the integral from a to b of f of x dx. And I'm going to say for any function f of x, that's actually not quite true, and I'll get to that. Basically, there are some kind of functions that this won't work for, but for the most part, this is the method we'll be using for most functions that we're going to be encountering. Okay, so now we're ready to introduce the fundamental theorem of calculus, part 2. So just like with fundamental theorem of calculus part 1, oftentimes you'll see it abbreviated as FTC, and now we're looking at part 2. So the fundamental theorem of calculus part 2 says, if you are evaluating an integral from a to b of f of x dx, that is going to be equal to capital F of b minus capital F of a, where capital F of x is any antiderivative of f of x. So basically, you're looking at the function on the inside, the integrand. You're finding the antiderivative of that function, and then you're plugging in the top bound and the bottom bound and subtracting them. So it is true that you can do this with any antiderivative, but generally speaking, the antiderivative that you want to use is one where c is 0. So I'll make a note of that, and then we'll jump into an example. So technically you can use any antiderivative, but really you should use the antiderivative with c is equal to 0. And I'll kind of point out what would happen if you would use a different antiderivative. You would still get the right answer, but you're just kind of making things more complicated than they need to be. So I want to look at a few examples to start with, and then I will show you the proof of the fundamental theorem of calculus, which basically we'll see part 2 follows from part 1. So yeah, we'll do some examples, see the proof, and then I want to do a few more examples after the proof, and especially I'm going to do some examples that bring up different things I want to illustrate. So, even if you're like, oh, okay, this is easy for me, I understand this, I would still watch the entirety of the video, just because I'm really trying to pick out examples to illustrate different specific properties of integrals and different types of situations that can emerge. Okay, so first example I want to look at is the integral from 0 to 3 of x squared dx. So when you're doing, when you're evaluating integrals now, you don't need a graph, because basically all you have to do is find the antiderivative and plug numbers in. I'm just pulling up the graph because I want to make sure that you're still connecting it to this idea of area. So first example we're going to do, like I said, is going to be the integral from 0 to 3 of x squared dx. So I picked this example because we actually already approximated this one in some earlier videos, and we found that using rectangles and we went on Desmos and we increased the number of rectangles, and we saw that it looked like the area was approaching 9. And so now we'll actually see that that is the true area. So the area that we're actually finding in this example is this area here. Okay, so how does this work? Basically, you just take the antiderivative of the integrand. So what's the antiderivative of x squared? Well, it could be capital F of x is equal to x cubed over 3. And then, usually you would say plus c, but we really don't need the plus c. And again, let's do it first without it, and then I'll show you what would happen if you tried to include plus c. But this FTC basically works with any antiderivative, so you might as well choose the simplest one. Okay, so what we're going to do is we're going to take this antiderivative, and there's some special notation I'm going to show you that is very commonly used in calculus, which is I'm going to put my antiderivative here, and then I'm going to put this vertical line next to it, and I'm going to put 3 at the top and 0 at the bottom. And that's basically just a shorthand way of saying that we're going to take this function here, evaluate it at 3, and then from that we'll subtract evaluating it at 0. Because this is a pretty simple example, but later on we'll be dealing with examples where the actual antiderivative is going to be rather challenging to find. And so you want to be able to write down the antiderivative and then also keep track of what you're actually plugging in. So the first thing we're going to do is we're going to plug in 3 for x. So we'll have lots of 3's now. We'll have 3 cubed over 3. And then we plug in 0. And so we have 0 cubed over 3. And so what does this simplify to? Well, 3 cubed is equal to 27. And 0 cubed over 3 is 0. And so we end up with 27 over 3, which is 9, which is what we already knew that area was, but now we have really shown it. A couple of things I want to point out. So notice that when we plugged in 0, we got 0. That happens a lot. It happens when basically you have a polynomial, but it's not going to happen for every function. So you never want to assume that by plugging in 0, you get 0. Make sure that you're checking, what your actual function is. The other thing I just want to point out is that, this is pretty cool, I think. Like basically this area that's shaded in blue, nothing about it is linear, right? It has all these curved edges. It's kind of an unusual shape if you really think about it, but its area is exactly equal to 9. So, we have certain shapes that we know how to find the areas using geometry, things like circles and rectangles and triangles. And this isn't one of those shapes, but it still works out that area is a perfect integer. So I just think that's kind of interesting and worth pointing out. So I just want to quickly show you what would have happened if we had used a different antiderivative and just see that we get the same answer. But again, this is not really how you would do it. So I'll just make a note here. If you had used, and maybe I like to use red when I'm doing something wrong, but maybe this isn't really wrong, so I'll just do it in a different color. So if we had used a different antiderivative, like let's say f of x is equal to x cubed over 3, let's just say plus 5. So what would have happened in that case? Well, we would have had x cubed over 3 plus 5, and then we would be again evaluating that at 3 and at 0. And so we would get 27 over 3, that's the same thing we got before, plus 5, minus, and then when we plug in 0, we would get 0 over 3, so it's just 0, plus 5. And so notice that these 5s are going to cancel out. We have a plus 5 here, and we have this negative sign, so it becomes a negative 5. So we end up with just 9. So my point here is that if you were to use a different antiderivative, because you're using the same antiderivative when you're plugging in both of these values, if you have any extra c, it's just going to cancel out. So you might as well just never include a c. Just choose the antiderivative with c is equal to 0. Okay, let's do a couple more examples before we get to the proof. So I want to do an example that we actually already did earlier. So on one of the first worksheets for the quarter, you used rectangles to approximate the integral from 0 to pi of sine of x dx. So this area here. And let's see what happens when we do this. So we want to start by finding an antiderivative of sine of x. So an antiderivative And I won't always write this part out, but just to make sure we're all clear on how this is working. So an antiderivative of f of x is equal to sine of x would be capital F of x is equal to negative cosine of x, right? Because the derivative of cosine is negative sine. So in order to get positive sine, we need an extra negative on it. And so how do we actually evaluate this? We say negative cosine of x, and then we're going to plug in pi, and we're going to plug in 0. And so we get negative cosine of 0, negative cosine of pi is the top bound, minus negative cosine of 0. So make sure you're careful with your negative signs. I think like really using FTC2 is fairly straightforward, but there is a lot of opportunity to make arithmetic errors. So just be really careful. Whatever you get by plugging in the lower bound, you're subtracting that entire thing. So if the thing that you're subtracting is itself negative, you're going to end up adding. Okay, so what is cosine of pi? Well, let's think about the unit circle for a second. So cosine is always equal to the x coordinate when you go to an angle on the unit circle. So if you go to an angle of pi, the x coordinate is -1, right? So cosine of pi is -1. So we have negative -1. And then these two negative signs become positive, and then cosine of 0, well, that's just equal to 1, right? Because the x coordinate at an angle of 0 is 1. And so we end up with 2. So if you go back to that worksheet where we approximated this area using rectangles, what you'll find is that we approximated that it was 2. We used more and more rectangles, and we saw that those values got closer to 2, and now we know for sure that this area is 2. And again, I just think this is kind of remarkable, like cosine or sine of x, those are not functions that generally have a lot of integer values on them, right? Like this curve goes through all sorts of different heights, yet it still comes out to give you an area of exactly 2. All right, let's do one more example, and then we'll get into seeing basically why this theorem is true. So last example I want to look at is the integral from 2 to 6, of 1 over x dx. So in this case, we're looking at the area between 2 and 6. So that's going to be this area here. Okay, so what is the antiderivative of 1 over x? Well, let's write it as, actually, I'll just say antiderivative of, f of x is equal to 1 over x. So remember that if you have a function that is x to a power, for the most part you use the power rule, but there's one exception to that, which is when your function is 1 over x, the antiderivative is just ln of x. But one extra thing we have to put in here is it should actually be ln of absolute value of x. And that's not going to matter in this case, but basically we need to ensure that the domain, so the domain of 1 over x is all numbers except for 0, but the domain of ln of x is only positive numbers. So we put the absolute value there in order to guarantee that the input is positive. And so in this case, that's not really going to come into play, but in general, you do want to make sure you put absolute value bars around that. So how are we going to find our area? We're going to do ln of absolute value of x evaluated at 6 and at 2. So that's going to be ln of absolute value of 6 minus ln of absolute value of 2, which is the same as just ln of 6. So that's why I said it doesn't really matter in this case. So that would be our exact answer. Let's get an approximation for this. So let me just type it into my calculator. I forgot to do it ahead of time. So it's approximately 1.099. Let's say 0.99. So not too surprising that it's around 1, right? If you look at the part that we shaded, if you picture kind of adding those all up, it is believable that they could make up like one box in this graph. So one last thing I want to mention before we get to the proof of the fundamental theorem of calculus part 2 is one kind of statement about situations where we cannot use the fundamental theorem of calculus. So basically, FTC, so fundamental theorem of calculus part 2, only works if the integrand, the function you're integrating, f of x, is continuous on the integral, or sorry, on the interval from a to b. So what do I mean by continuous? That's something that you should have talked about in Calc 1, but basically you're looking for it to not have any jumps or gaps or holes or asymptotes. And really, like, all we'll be encountering for the most part is asymptotes. So I'll just write that down because that's really with the types of functions that we're working with, we're not really going to be encountering situations with like jumps in the graph. But we will see vertical asymptotes. So for example, if we were to try to integrate from -1 to 3, the same function that we just did above, 1 over x. So going back to this graph, that would not really work because we would be evaluating an integral that includes this vertical asymptote. And so the problem is that basically the graph goes up infinitely high around 0, right? And then it goes down infinitely low on the left side. So it just doesn't, it's not bounded. It doesn't really fit the same kind of characteristics as the other functions we've been looking at. So we'll actually learn how to evaluate integrals like this at the towards the end of the quarter. It's called an improper integral, and there's other methods. We basically have to use limits to deal with integrals like this. But basically for now, just know that FTC just doesn't work in these situations. There may be situations where it does work, but you cannot assume that it is going to work. So for example, this integral cannot be evaluated using FTC2 because there is a vertical asymptote at x is equal to 0, and that vertical asymptote falls between the two bounds, right? So in the example we did up here, it was okay because even though there is a vertical asymptote at 0, our bounds were 2 and 6, so it didn't fall between those two bounds. Okay, so let's get into the proof, and then after that, like I said, we'll do a few more examples which kind of show some different things going on with these integrals. Okay. So basically what we'll see is that the proof for FTC part 2, it basically just relies on FTC part 1. So we're going to assume that FTC part 1 is true. We didn't actually prove FTC part 1, and just kind of to maybe let you know what to expect in this class, I'm not going to be proving every single thing that we learn in this class. I'm going to be kind of choosing which proofs to show you based on which ones I think are maybe interesting or illuminating or not too hard, things like that. So we're just going to assume that FTC part 1 is true. And I think we had evidence for it, right? Because we did that worksheet and the problems involving the area function, and we saw that FTC 1 appeared to be true. So hopefully you believe that it is actually true. So what are we trying to prove here? So we want to show, so maybe just to speak generally about proofs, what's the idea of a proof? It's basically to take things that you do know and kind of follow some logical steps, whether that includes algebra or other kind of things, and follow those logical steps until you show something new. So in this case, what do we want to show? We want to show that if you take the integral from a to b of f of x dx, that is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, where capital F of x is any antiderivative. of little f of x. And what are we going to go off of? Well, we're going to use FTC 1, like I said. So FTC 1, just to remind you, it says that if you have an area function, so I'm going to use capital G in this case. So if you have an area function where you're doing the area from some lower number to x of f of t dt, then the derivative of this area function is equal to your integrand. It's equal to that function inside, just switching the t for an x. So basically, another way of saying that would be that g of x is an antiderivative of, and I'll just say f of x. Again, don't worry too much about this tx thing. It doesn't really matter what variable we're using, but you could just say, if you wanted to avoid the variable issue, you could just say g is an antiderivative of f. So you might already start to see there's some connection here, right? So the, what are we trying to show? We're trying to show something about relating the integrand to an antiderivative of that integrand, and we're already kind of seeing something like that happen. I'm just going to change the color of this so that it, stands out a little bit. Okay, so what we're going to do is we're going to take this, this area function and we're going to plug in the number b. So what happens if we plug in the number b? So if we evaluate this area function at b, we get the integral from a to b of f of t dt. So all I did is I literally just took this x and I just plugged in b. But now that there's no x's in this anymore, we could, if we wanted to, rewrite this integral as the integral from a to b of f of x dx, right? Because again, it really doesn't matter what variable you use here and here, as long as they match. So we can just for the sake of kind of having things look the way we want them to, let's just change it to an x. There's nothing wrong with doing that. And then what about if you plug in a? So, little a. Well, if you plug in little a, you get the integral from a to a of f of t dt. And so one thing that we discussed in an earlier video is that that integral is always going to be 0. And actually, I'm going to put a question on today's worksheet where you'll actually show that the integral from a number to itself will always give you 0. So putting these together, well, what do we get if we do g of b? Let me maybe say, so g of b minus g of a, according to what we just wrote down here above, that's going to be equal to the integral from a to b of f of x dx minus 0, which is just the same as the integral from a to b of f of x dx. So at this point, we're almost there, because what did we just show? We just showed, so remember that g is an antiderivative of f. So we just showed that the integral from a to b of f of x dx can be expressed as g of b minus g of a, where g is an antiderivative. So I'll make a note of that. G is an antiderivative of f of x. However, it's a very specific antiderivative, right? It's the area function antiderivative. And we want to show that this is true for any antiderivative. So there's kind of one more step that we need to take to really finish off this proof. So we want to show that FTC2 works with any antiderivative of f of x. So how are we going to do that? Let's just let capital F of x represent any antiderivative. So let capital F of x be any antiderivative. So just some arbitrary antiderivative of f of x. So one thing that we know about antiderivatives, and I talked about this in the very first video about antiderivatives, is that if you have two different antiderivatives of a function, they're going to differ by a constant, right? Because of this plus c business. So if f of x is an antiderivative and g of x is also an antiderivative, that means that we must be able to write f of x as g of x plus c for some number c. We don't need to know what that number is, but there's some number out there that is the constant that relates capital F and capital G. Okay, so now we're really ready to finish this off. So let's say that now we want us to write down f of b minus f of a, right? Because that's what we wanted to show, was just any antiderivative. So what's another way of writing f of b minus f of a? Well, f of b would be the same thing as g of b plus c, right? Basically coming from this fact. So based on that fact, we can rewrite f of b as g of b plus c. And then for f of a, similarly, we can write that as g of a plus c. And so this simplifies to be g of b. And then just like actually happened in that earlier example, it's a really similar idea. These constants cancel out. And so we're left with g of b minus g of a. So this does not mean that f and g are the same function. What this means is that if you're subtracting f of b minus f of a or g of b minus g of a, it basically doesn't matter what antiderivative you use. And so earlier, we just showed that FTC2 was true with this one specific choice of antiderivative, but now we know that capital G of b minus capital G of a is the same as capital F of b minus capital F of a. So now we can conclude, and this is our last statement here, we can conclude that capital F of b minus capital F of a is equal to the integral from a to b of f of x dx. And that is what we wanted to show, right? That is the fundamental theorem of calculus part 2. Okay, so let's now look at a few more examples. So like I said, I want to do a few examples to kind of illustrate some different properties of integrals. And then I also want to do an example that is just a little bit more complicated in terms of the antiderivative, like actually finding the antiderivative, because as I mentioned, that will kind of be the main challenge for a lot of these problems. And we'll see that happen more and more as we go throughout the quarter, is problems where the antiderivative itself is kind of tricky to calculate. Okay, so let's say we wanted to evaluate the integral from negative pi to pi of sine of x dx. And we'll look at the graph in a second, and we'll see that actually, if you just looked at the graph, you could answer this question without using FTC, but let's say that you forgot about that, or you didn't know that. So forget the graph for a second. Let's just evaluate this integral just using FTC. So we already did something similar, right? We did the integral from 0 to pi. So we know that the antiderivative of sine of x is negative cosine of x. And this time we're evaluating that at pi and at negative pi. So let's, again, draw the unit circle. Maybe I'll just draw it here to figure out what cosine of pi and negative pi are. So pi is this angle here, right? And so we get an x-coordinate of -1, 0. But negative pi is actually the same. It's not the same angle, but it's the same, gives you the same point. And so cosine of negative pi is the same as cosine of positive pi. So when we go to plug these numbers in, we get -1. That was the first part. And then, and actually maybe let me write out one more step just so that you don't lose yourself in this arithmetic or algebra. So we have negative cosine of pi minus negative cosine of negative pi. So a lot of negative signs going on. And so negative cosine of pi is going to be -1. And then this becomes a plus. And then cosine of negative pi is going to be -1. I know that's a little confusing with all the negative signs. But so this turns out to be 1 minus 1, right? And so we get 0. So how could we have been able to tell that that integral was equal to 0 without actually going through and evaluating it? Well, looking at this, the graph of sine of x, notice that if we're going from negative pi to pi, we have one part of the graph that is below the x-axis and one part that's above, and they're equal areas to each other, right? Because of the symmetry of the graph. And so basically the positive and negative parts are canceling each other out. And so that's why we get 0. So why did this happen? What is it about this function that caused us to get 0? Well, it's because this is an odd function, right? F of x is equal to sine of x is an odd function. And odd functions display this kind of symmetry that we see in this picture where we're having kind of the opposite thing happen when you go this way compared to this way, right? Like I like to think of odd functions as almost having like a pinwheel shape, right? If you look around the origin, they have this shape where they're kind of mirroring each other both horizontally and vertically at the same time. So anytime you have an odd function, so in general, if f of x is an odd function, so maybe just to quickly remind you, I'll just put this note here. So an odd function is any function that is symmetric about the origin. And another way of defining an odd function is that f of negative x is equal to negative f of x. So if f of x is an odd function, then it's always going to be true that the integral from negative a to a of f of x dx is going to be equal to 0. And that's just because, again, you'll get this behavior where there'll be a positive part of the graph and a negative part of the graph, and they'll cancel each other out. So why am I telling you this? Because basically in the future, if you encounter an odd function, you don't actually need to evaluate the integral. If you can recognize that it's an odd function and then tell me that, then you don't need to do anything. You can just say it's an odd function. Therefore, the integral from negative 1 to 1 or negative pi to pi or negative 5 to 5 or whatever the numbers are, it's going to be equal to 0. So let's now take a look at what happens when you have an even function. So now let's go back to our function f of x is equal to x squared. So we're now going to look, instead of doing the integral from 0 to 3, we're going to do the integral from negative 3 to 3 of x squared dx. So again, we can do take the antiderivative, so we get we get x cubed over 3, and we're going to evaluate it now at 3 and at negative 3. So when we plug in 3, we get 3 cubed over 3, and when we plug in negative 3, we get negative 3 cubed. I guess I didn't need that extra parenthesis. Let me just take that out. Negative 3 cubed over 3. So 3 cubed over 3 is 27 over 3, or 9. And then negative 3 cubed over 3 is going to be negative 27 over 3. And so when we add these together, we get, so 27 over 3 is 9, and then we have minus negative, so that's plus. So we have 9 plus 9, which is 18. So notice that that is twice the value that we got from 0 to 3. And if you just look at the picture, that makes lots of sense, right? Because if we're doing the integral from negative 3 to 3, that's just doing 2 times the area from 0 to 3. So in general, anytime you're evaluating an even function, so if f of x is an even function, so again, I'll quickly remind you of what I mean by even. So an even function is a function where it's symmetric about the y-axis. So just like f of x is equal to x squared, And another way of saying it is that f of negative x is equal to f of x. So you get the same result by plugging in a negative or positive number. So anytime f of x is an even function, then the integral from negative a to a of f of x dx is going to be equal to the same thing as doing 2 times the integral from 0 to a of f of x dx. And this is actually a really useful fact. This is going to come up quite a bit. And the reason it's helpful is because it's generally easier to plug 0 into an antiderivative, especially when you get these more complicated antiderivatives. And we'll see that there's going to be some kind of there's going to be a lot of fractions, I'll put it that way, when we're evaluating these. And oftentimes, the numbers are not so much fun to work with. And plugging in 0 is just way easier than plugging in a different number. And so if you can find a way to rewrite your integral so that you're only plugging in 0, you're not plugging in 2 different numbers, then that's going to make your life a lot easier. So if you can recognize that something's an even function, then you're allowed to evaluate the integral this way. Okay, just a couple more examples I want to do. So I want to look also at the following. So let's say that we were evaluating the integral from 3 to 0 of x squared dx. So you might notice that something's a little bit funny about this integral, which is that the bounds are flipped from what you would expect, right? Usually we put the smaller number on the bottom and the bigger number on the top. So if you remember back to the properties of integrals video, we talked about how if the bounds are switched, it's going to be the negative of what you would get by having the bounds the other way. So I want to show you that actually, even without knowing that rule, it's going to come out that way. So let's say that we were trying to evaluate this integral and we didn't realize that we could just switch the bounds and flip the sign. We just were doing it kind of as is. So we would still say we're taking the antiderivative, so x cubed over 3. Now we would be plugging in 0 first and then 3. So how is this going to work out? Well, when we plug in 0, we'll just get 0. And then we'll be subtracting 3 cubed over 3. So this is now going to be 0 minus 27 over 3, which is equal to negative 9. So notice that is the negative of what we got earlier when we did the integral from 0 to 3. And hopefully you can see why, right? It's just because you're subtracting in the opposite order. And if you subtract 2 things in the opposite order, the sign will flip. So basically from here on out, if you have a situation like this where your bounds are kind of in the quote unquote wrong order, you have 2 choices. You can either evaluate it as is, and that way you will get the right answer. If it feels better to you to just switch them, then all you have to do is flip the sign. So either way will work. All right, one last example, and this is just going to be kind of a typical, more complicated example. So the earlier ones we did were more to kind of illustrate different properties. This is just going to be a more kind of straightforward, let's just evaluate the integral. So let's say we were trying to evaluate the integral of square root of x plus 1 all over x squared dx. So this is an example of one where, finding the antiderivative is a little bit more complicated than it was in the earlier examples. So this goes back to an idea that I've been pushing since Calculus 1, which is that if you can simplify a function before taking the derivative or antiderivative, your life is generally going to be easier. And especially in this class. So it's going to be very, very important. Like in Calc 1, there would be problems I would give you where it's a function like this, and I asked you to take the derivative. And some of you remembered that you could split it up and then take the derivative. A lot of you tried to use the quotient rule. It works when you're taking derivatives, right, to use the quotient rule, but there is no reverse quotient rule. So when you're taking antiderivatives, you really have no choice but to simplify this before trying to take the antiderivative. So we want to rewrite this as the integral from 1 to 3 of, so let's split this into 2 fractions. So we can rewrite this as x to the 1/2 over x squared plus 1 over x squared. So why is that useful? Well, because then we can simplify each of these two fractions in a way that we can use the power rule or the reverse power rule. So x to the 1/2 over x squared, we want to do 1/2 minus 2. So that's going to give us x to the -3/2. And then we can rewrite 1 over x squared as x to the -2. Okay, so now we're ready to actually evaluate this. So to evaluate this, we want to take the antiderivative. So how do we take the antiderivative of x to the -3/2? Well, we start by adding 1 to the exponent. So -3/2 plus 1 is going to give us -1/2. And then we take the reciprocal of our new exponent. And so the reciprocal of -1/2 is -2. And then we have x to the -2, and so that we add 1 to the exponent, and we get x to the -1. And then we take the reciprocal of -1, which is just -1. And then we're going to take this whole thing, and we're going to, I guess I don't really need the parentheses. We're going to evaluate this whole thing at 3 and at 1. But let me just write this a little bit nicer. So we have -2 x to the 1/2. Minus x to the -1, and we're evaluating that at 3 and at 1. Okay, so what is this going to look like? This is where, the fractions are going to come in. So here, when we plug in 3, we're going to get -2 times the square root of 3. And then we're going to have minus, and so if we plug in 3 for x here, we'll have 1 over 3. Now we have to subtract what we get by plugging in 1. So when we plug in 1, we'll get -2 times the square root of 1, but square root of 1 is just 1. And then from that, we'll subtract, plugging in 1 to the second part, we'll get -1. And make sure you put parentheses. This is so important. If you don't put parentheses here, you'll get the wrong answer. So whatever, like when you're plugging in this bottom bound, you need to put parentheses around the expression when you're plugging it in and distribute the negative sign. So altogether, we get -2 root 3 minus 1/3 plus 2, or actually let's do this stuff in the parentheses first. So -2 minus 1 is equal to -3, and so we have plus 3. And so we can make a common denominator with this -1/3 and this 3, so we have minus 1/3 plus, so 3 we can write as 9 over 3. And so we're left with -2 root 3 plus 8 over 3. And that would be our final answer. And I guess this one actually, the fractions didn't come up as much as I maybe anticipated, but you will definitely see cases of dealing with a lot of fractions. So I'll put some on today's worksheet that will get into that a little bit more. All right, so that is it for today, and I will see you all in the next video.